unit cells. Okay, in chapter 3 we talked about unit cells from a geometrical point of view to identify direction, points, and planes. But we haven't introduced atoms till we have basically we introduced chapter 4. We started populating atoms into the unit cells. So this is something that we done at the beginning. And from there, we took it and we were able to calculate how many atoms per unit cells. So within each unit cell, how many atoms are there. And then we were able to find out the coordination number, meaning that the nearest atoms, we were able also to find out the coordination, the number, and the atomic packing factor, which is basically describe how dense the unit cell is. So these are basically at the beginning of chapter 4. We have discussed them. We found out that the atomic packing factor of the FCC, which is the face center cubic, has the highest atomic packing factor, the most efficient packing. And we found out also that the hexagonal closed pack system has the similar, or the same actually, the same atomic packing factor. And it was not a coincidence, since we showed last time that FCC and HCP, FCC face center cubic, HCP hexagonal closed packed. So the FCC and HCP share something. They are made of closed packed plane. The only difference is the sequence of these closed packed plane. In the case of the FCC, we were talking about the ABC, ABC, ABC sequence, but for the HCP, it was AB, AB, AB sequence. So this is something that we have talked about. Also, we talked about polymorphism or allotropy, meaning that a single material can have more than one crystal structure depending on the environment. We gave an example of the iron. We gave an example also about diamond and graphite or carbon. We talked about the titanium as well. And also, most importantly, we were talking about the unit cell. And one of the reasons that we study unit cells is because if you study them, you can basically generalize the behavior of the whole material based on the unit cell. And we compute the density. From the unit cell, we computed the density of the material based on just the unit cell. So picking up from there, let's try to solve this example. So he's asking to calculate the radius, okay? To calculate the radius of vanadium atom, given that V has a BCC crystal structure and the density is 5.96 grams per centimeter cube, and the atomic weight is 50.9. Let me remind you about the equation. So the first thing is to write the equation, okay, to know what's known, what's not known, okay? So the density is equal to NA over VC NA. Here, the rho is the density, N is the number of atoms per unit cell, and A and A here is the atomic weight, V is the cubic, the volume of the cube, and Na is the Avogadro number. So let me ask you from the question, do we have the density, ya shabab?
Yes.
Yes, we have the density. Do we have N, the number of atoms per unit cell? Do we have it?
Not yet.
BCC.
BCC. So what is N for BCC? Do you remember, Shabab?
Sure.
2.
We will draw.
Yeah, it's 2. So we have done it last time. So the gentleman who said not yet, no, we know it, okay? Because he's saying the BCC crystal structure, and we know that for BCC it has 2 atoms per unit cell. For FCC, how much is it for FCC?
4.
4. And for simple cube?
1.
1. Okay. So N, we know it. Atomic weight, do we know it?
Yes.
Yes. What about the Avogadro number?
Known.
Yeah, no.
Known. Okay. So the only thing missing is VC, which is the volume of the cube. So what is يا شباب? Sorry. Okay. So what is VC? What is the VC? The volume of the cube. Do you remember, شباب?
The mass over the density.
Mass over density. This will give you what? The volume, correct. But also we know from the cube, we can find out the volume. صح ولا لا? Remember, for the cube. We said that if this is A, what is the volume then?
A cube.
A cube. صح ولا لا? So this is something that we have done before, okay? We have done last time. So the volume of the cube is equal to A cube. But since he's asking about the radius, okay, not asking about the edge length, okay, he's asking about the radius. We also did something last class, which is to find out the relationship between the A and R. And I refer you to the last lecture, but we found out that the A is equal to 4 over square root of 3 R. Okay, so this is something that we derived last time, the previous lecture. So A cubed equal to 64 over 3 square root of 3 R cubed. Okay, which is the same as VC. So now we plug it here. So we say that the rho, let's change the color. The rho is equal to 2 atoms, and it's very I advise you, Shab, to write the units, okay? Always write the units. So rho is equal to before that. Okay, sorry. So rho is equal to NA over 64 over 3 square root of 3 R cubed NA, meaning that the R is equal to 3 square root of 3 NA over 64 rho NA to the power 1 over third. Okay, so meaning that the R is equal to 3 square root of 3 N, which is 2 atoms, times A, which is the atomic mass, it's already given, 50.9 gram per mole, divided by 64. Density is already given, so 5.96 gram per centimeter cubed, times NA is already given, 6.022 times 10 to the power 23 atom per mole. So you see, guys, what I did is to write the units of all the numbers. Why? Because just to avoid any confusion. When I say confusion, meaning that sometimes you will find a number in gram and here in gram, but here in kilogram. Just to avoid this kind of mismatch, it's better just to write the units clearly so you can decide. So from here we can cancel, of course, the moles, we can cancel the atoms, we can cancel the gram, and we will find out the R. And here R, what will be the unit of the R here, Shabab?
Meter or centimeter.
Centimeter.
Okay, centimeter. Centimeter. طيب. Okay. I'm trying to find out the exact value of the R. Just give me a minute. So we can calculate, and we will find out that the R is equal to 1.32 times 10 to the power minus 8 centimeter, okay? Or R is equal to 0.132 nanometer. And this is the answer. طيب أي سؤال يا شباب؟ طيب
دكتور
تفضل.
معليش هل تستخدم وحدة الأرمسترونج؟ ما يستخدم.
It's up to you. Sometimes the question will not ask. For example, here he's asking to find the calculated radius. He did not say anything about the units. صح ولا لا? Sometimes you'll find the question he's asking you specifically to find out in terms of specific unit. Okay. So in this example, so what will be the angstrom then?
1.32.
1.32. So angstrom is 10 minus 9, isn't it?
No, minus 10.
Minus 9 is nanometer and minus 10 is angstrom. Okay, so it will be, I think, 1.32 or 0.132. Let me check. Yeah, so basically it will be 1.32. Yes, 1.32. So minus 8.
أنا قصدي بس إن الشائعة الأكثر استخدام.
Okay. Nanometer is most common. Angstrom and nanometer both are used, to be honest. So it's up to you.
تمام. شكرا.
Okay. طيب. Linear density. So this is the last portion of chapter 4. So we have talked in chapter 3 about the direction and planes. In chapter 4, we talked also about how to find the magnitude of that direction. Okay, when we basically found out the relationship between the A and R. So simply, the linear density is the number of atoms per unit length. Okay, the number of atoms per unit length. And the number of atoms is the centers that lies in the direction vector. So for example, if you look at here, we know that the linear density is the number of atoms per unit length, okay, for the length of direction. So the number of atoms in this case, for this direction, which is here, which is 110, okay? You see this is the direction if you consider a 2D. So how many atoms are there, Yashab, crossing whose center are on the line direction? So we find out that this is R. So this is this is an R, not a whole atom, and this is here we have 2R, and here we have an R again. It's not a complete atom, okay? So how many atoms are there, Shabab?
2.
Exactly. So we have 2 atoms here. And then from the direction, do you remember how did we derive such a direction, Shabab? So this is A, and this is A. صح ولا لا شباب? So what will be the value of this direction, شباب?
Two X.
ها تفضل.
Root 2.
Root 2A, صح? So this is the magnitude of this direction. So it's root 2A. Shabab, if there is something unclear or you need me to clarify, please let me know, okay? I'm not spending much time here because we have done it in the last lecture. I mean, we derived everything. But this is root 2 or from Pythagorean theorem, okay? So this is basically the linear density now. Let's try to solve this example then. And before that, remember from last chapter, we talked about the family of directions, and we said that the family of directions contains directions which are equivalent. But we haven't talked about the equivalent meaning. Equivalent meaning they have the same or identical linear densities, okay? So if you have directions with the same linear densities, that those directions belongs to one family. So let's try to solve this example here. So he's asking to find the linear density of aluminum in this direction, which is 1, 1, 0, okay? And he's giving you the A, which is the unit edge length. So in this direction, again, we have 1R, we have 2R, and we have R here. So meaning that we have 2 atoms now. And we said that this is A, meaning this one here is square root of 2A. So if he gives us the radius, then we need to convert A to radius. But here is already giving you the A, so we don't need to do that. So we need to square root of 2A and substitute A to find out the answer. So basically, it's the number of atoms, which is 2. The length is square root of 2A, and substitute to find out the number is 3.5 nanometer to the power minus 1. We'll solve another example in a minute, okay? But before we solve another example, let's talk. We talked about the linear density. Also, we have something called the planar density, which is again the same thing. It's the number of atoms per unit area. And the number of atoms, we quantify it within enclosed that area, if it's enclosed within that area. So it's the number of atoms divided by the area of the plane. Let me give you an example. And before that, it's a similar thing. We talked about the family of planes. And we said that the family of planes contains planes that are equivalent. Equivalent means that they have the same or identical planar densities. So take an example of iron, okay? Has a BCC structure. So it's something like this. So he's asking you about the plane 100. So plane 100, it's here. It is this plane here. So if you try to propagate this plane here, you will find out something like this. Can you imagine it, Shabab? So if you propagate this plane here and draw a 2D diagram, it will be something like this. Or more clearly, it will be something like this, okay?
Mm-hmm.
And you see that we have, how many atoms are here, Shabab? Enclosed within the plane itself?
One.
Just one, okay? Because each one is quarter in this case, okay? So this is 1/4, 1/4, 1/4, 1/4. So if you add them up, it will be 1. So the planar density in this case equal to 1 over. So what is the area of this one, Ishaq? So we know this is A and this is A. So what is the area? What is the
A squared?
A squared, exactly, A squared, okay? So it's A squared. But we can basically relate it to the R here. So because he's giving us the R. So we know that from the BCC is 1/4R over square root of 3 squared. And we can basically substitute. So it's basically this one squared. You find out the number is 12.1 atom per nanometer square, or 1.2 times 10 to the 19 atoms per meter cube. Okay. أي سؤال يا شباب؟ Good. So let's try to solve an example here. So he's asking you to derive a relationship, a linear relationship, a linear density expression of FCC and these directions in terms of the atomic radius R. So this is an FCC. And let's focus only on this direction, okay? 111. 111 meaning that it will start from here and stop right here, from the back to the front here. So this is 111. And the linear density we know is the number of atoms divided by the length of direction vector. So what is the number of atoms here? How many R do we have? What do you think, guys?
1
Any
and
guesses?
quart.
1 and quart. Okay, why is 1 and quart? What do you think? So do we have? So we are starting from here and starting here. So how many R? So here, how many R do we have? We have 1 R. Okay, because this is at the center of the origin, and we are talking about the origin, so 1 R only. And here we have 1 R. Now the question, does it pass through any other atom here?
Yes.
This is, huh?
هل نحسب دكتور اللي فوق الأوريجن بشوي؟
You mean this one here ولا this one؟
No.
طب هذه وين متواجدة هذه؟ Where are those? Where are they? So they are on the faces ولا they are inside the unit cell? This is an FCC. The face center cubic, they have the atoms on the faces, okay? They are on the faces, not within the cube itself. BCC, we have a complete atom within the cube. But for the FCC, all these atoms are on the faces. And we are talking about cutting the unit cell through the diagonal. So within the body, within the unit cell itself, from the back to here. So again, my question, does it pass through any other atom?
No.
No. So how many atoms do we have here? We have 2R, meaning that how many atoms do we have?
1.
Just 1, exactly. We have 1 atom. Is it clear to all of you, Shabab? Should I repeat it? Okay, fine. So the length of the vector. Now we know this is A, this is A, this is A, and this one here is square root of 2A because it's from Pythagorean theorem. And we know this one here, this is square root of 2A, and this is A, and we know this one here will be a square root of 3A. Again, if you have a question, you can ask, but also you can go back to the previous lecture where we explained, we derived how to do this, okay? So this is square root of 3A. So this is the direction, so it's square root of 3A. So we can stop right here. This is the correct answer, but he's asking you in terms of the atomic radius, okay? And for face center cubic, A is equal to 4 over square root of 2 R. Meaning that the linear density is equal to 1 over square root of 3 4 square root of 2 R. We can simplify it. 1 over 3 times 16 divided by 2R, which is equal to 1 over 3 times 8R, which is equal to 1 over 2 over square root of 6R. So this is the answer. أي سؤال يا شباب؟
يس دكتور، أنا عندي سؤال بفهم السؤال.
تفضل راحتك.
يوم كتب هنا 100 كان يكتب
ايش؟ 100
يس
100 يعني زي كذا صح؟
ايه.
طيب كم اتم؟
يعني هو الآن السؤال مقسم إلى قسمين 100 111.
اي two different parts, two different. Okay.
ايه خلاص اوكي كذا
وضحت؟ طيب 100 how many atoms here؟
the same.
It will be 1 صح؟
Yes.
Because we have here 1R.
Right.
Now the story will be different if it's something like this, okay? Like we have done as we have seen before. طيب, let's talk about the planar density. And again, let's focus on the 111 plane. We don't care about 110 because it's simple, okay? So it's 111 plane. So 1, 1 on plane, it will be something like this. Okay. Okay, it will be something like this. And if you try to draw it in 2D, it will be something like this. So here, this is the base, which is this one here. It has 4R, 1R, 2R, 1R. And here also we have 4R, and here we have also 4R. Can you see it, Shabab? Can you imagine it?
Yes.
Okay. Now, my question to you is, how many atoms are there? So from this diagram here, so we are talking about these. How many atoms do we have here?
4.5.
4.5. Okay.
Maybe 3 in total.
3 in total. Okay. Let's see. Okay, let's start from the beginning, from the simple thing. So this one represents how many atoms? Just this one here.
Half.
Just half, صح ولا لا? So how many halves do we have here?
3 halves.
3 halves, صح ولا لا? طيب, this is good. So what about this one here?
Maybe 1/3.
So for sure, it's not half. صح ولا لا?
Yes. And it's
For
not
sure, it's not 1/3. I'm going to go 1/3 and something like this.
yes.
Maybe.
Below that.
And for sure, it's not 1/4. صح ولا لا? 1/4 is like this. صح ولا لا? So it should be lower than that one. Okay. And this is, since this is a triangle, okay, so this is 60 degrees. So this one will be 1/6. Okay, this portion here will be 1/6. So how many do we have 1/6?
3.
3. Meaning how many total number of atoms?
2.
2 atoms. Do you get it, guys?
Yes, Doctor.
Okay.
Yes.
Right. 2 atoms. Okay, this is the first part. Now we need to find out the area of the plane. So for a triangle, what is the area of triangle? Any general triangle, what is the area of it? نصف القاعدة في الارتفاع, صح? So half base height. So the base here is what, يا شباب? What is the base? What is the value of the base here?
4R.
4R. The height, we can find it out. This is the h. And apply Pythagorean theorem here. We know that's 4R squared is equal to 2R squared plus h squared. Meaning that the h is equal to 12R squared, meaning that the h is equal to square root of 12R. So we can put here also square root of 12R, meaning that we can cancel out this one here. So it will be 2 square root of 12R. We can even simplify it further. I mean, this one is 3 times 4, so we can say it's 4 square root of 3R squared, sorry, because it's an area. Finally, we find out the planar density. We say that it's 2 atoms, and the area is 4 square root of 3R squared. So we can cancel out these things. So 1/2 square root of 3R squared. So this is the planar density. كلير يا شباب؟
ايه دكتور.
طيب اي سؤال عندكم يا شباب؟